Let's look at an example in a minute. First, look at two variable function. The Hessian is the double derivative to x, y. That's the shorthand of this and this. The third one is fyx. Last one is this. So if you look at the determinant, you see it equals this. Fx, x, fy, y means the second derivative to x times second derivative to y minus the mixed derivative square. If it's positive, then we know it's going to be either minimum or maximum. So which is which? If A, that one is positive, then you got the minimum. And when the A is negative, in this case, you got the minimum. Remember, y is a number. When you have x, y equals, let's say A, y equal B, because the P0 is a particular point. You're going to see that from the example. On the other hand, if the determinant is negative, you have neither minimum nor maximum. It's going to be the behave like this. And we can check the three cases easily. Let's check this determinant quickly. In the first case, let me extend the page. I wanted to, yeah, okay, good. For the case A, the gradient is going to be 2x, 2y. The Hessian matrix is going to be 2, 0, 0, 2. And your determinant is really 2, 2, 0, 0 equal 4. That's it. For the B, the same thing. H just have a negative. The delta equals negative 2x. Let me erase. And the B, the delta is negative 2x, negative 2y. The Hessian matrix, take the double derivative, take this to x, negative 2. Take this to y, 0. That's 0, negative 2. And then D equals, it's going to be 4 again, positive. See, the difference is the A. Where's the A? This is the A. This is positive, then the first you got the minimum. And this one, the A is negative, you get the maximum. Now look back. See? This one, we got the minimum here. And this one, we got the maximum here. I mean, this one, we got the minimum here. And this one, we got the maximum here. So that's the baseline, give you the sufficient condition. Look at the saddle surface. You look at the gradient at the D, which is going to be y and x. At the point origin is 0, 0. Look at the Hessian. I hope you still remember the Hessian. Take the derivative to x, that's 0. Take it to x, that's 1. And take a y, that's 1. Take it, that's 0. And then your D equals this, which is negative 1, negative. So that is a saddle. Okay, let's continue. So the sufficient condition is determined by two signs. The first is the D, positive or negative. The second is the A. Only when D is positive, you get the optimization. And if d is negative, you don't get anything. Now let's look at the second example. The first example is all baseline. In this example, the f equals xq plus yq minus 3xy. In order to get the Hessian, first take the gradient. Take derivative to x, that's 3x squared minus 3y. And take a derivative to y, 3y squared minus 3x. Where you're going to find the critical points? We remember you want to set this equal 0, 0. And then you got the two equations. And that's not hard to solve. You only got the two solutions. Either 0, 0, let me call this point as P1. And the P2 is going to be 1 and 1. You plug it in. See, 0 equals 0, that's good for both. And the 1 is both, it's good for both. And then at these 2 points, what's next? You need to get the Hessian matrix, right? And the Hessian matrix, take a derivative to x and to y, that's 6x. And if you take a derivative to y, that's a negative 3. And take this to x is negative 3. Take it to y, that's 6y. And then this is a matrix. The determinant is going to be 6x equals 36xy minus 9. Okay, so that don't give you a number. When you plug in the point here and here, you're going to get a number. So let's see what a number I get. To put the point 0, 0, and your A is, let me think, what's the A? If it's 0, 0, okay, A is 0. A is 0, D is negative 9. That's enough to tell you it's a saddle point. And that point is right here. Can you see it? The saddle point. And you go down this way, it's down. And this way is down, but another direction is up. Okay, that's the saddle point. The second point, 1, the 1, the D, you remember, is 36xy minus 9. Then 36 times 1 minus 9. That's 36 minus 9 equal 27. It's positive. And your A is positive. So what you get? You got this point right here. Right here, A minimum. Okay, we spent enough time to review what you learned the most in calculus. But the difference I want to show you is the connection to the Taylor series. Locally, for the last example, in the point P1, 0, 0, you can see the quadratic term is pretty much like the x squared minus y squared. That's a saddle point, because this is 0. And for the second point, P1, P2, 1 and 1, the behave for this second quadratic term is more or less like x squared plus y squared. And what you get is a minimum. So the only thing I want you to pay attention is to connect to the Taylor series. when I always say local behavior, what it means local behavior? Means in the very near neighborhood, you look at the graph. And so we give you the Lagrange's method without any constraint so far. It's the traditional maximum and the minimum.